Yes, indeed, these are the strings of the universe. They are hardly like the strings we imagine. In string theory, they are incredibly tiny, vibrating threads of energy. These threads are more like minuscule rubber bands, capable of twisting, stretching, and compressing in all sorts of ways. According to theorists, everything that exists is made up of these threads. So what exactly are these strings? Let's delve in from the very beginning. In the second half of the 19th century, physicists thought there was nothing significant left to discover in their field. Classical physics believed it had no major problems left, and the entire structure of the world seemed like a perfectly tuned and predictable machine. The dawn of quantum mechanics and its conflict with relativity. However, calculations for the energy radiation of a black body, a body that absorbs all incident radiation at any temperature, regardless of wavelength, showed that the total radiation energy of any black body should be infinitely large. In 1900, German scientist Max Planck hypothesized that visible light, X-rays, and other electromagnetic waves could only be emitted in discrete packets of energy, which he called quanta. This idea successfully solved the specific problem of the black body. Later, in 1926, another German scientist, Werner Heisenberg, formulated the famous uncertainty principle. Its essence is that nature limits our ability to predict the future based on physical laws. This, of course, refers to the future and present of subatomic particles, which behave entirely differently from anything in our surrounding macroscopic world. The behavior of subatomic particles is so turbulent and incomprehensible that it defies common sense. Space and time within it are so curved and intertwined that there are no usual concepts of left and right, up and down, and even before and after. There's no way to definitively know the exact point in space where a particular particle is at a given moment, or what its momentum is. There's only a certain probability of finding a particle in multiple regions of spacetime. Particles at the subatomic level seem to jump across space. In general relativity, the situation is fundamentally different, like a state with contradictory laws. Space is envisioned as a trampoline, a smooth fabric that can be bent and stretched by objects possessing mass. These objects create spacetime deformations, which is what we perceive as gravity. It goes without saying that the coherent, regular, and predictable general theory of relativity is in an irreconcilable conflict with the chaotic hooligan of quantum mechanics, and consequently, the macroscopic world cannot reconcile with the microscopic world. The promise of string theory. This is where string theory comes to the rescue. Many scientists are confident that everything, from the elegant dance of galaxies to the frantic dance of subatomic particles, can ultimately be explained by just one fundamental physical principle, perhaps even a single law that unifies all types of energy, particles, and interactions into some elegant formula. The theory of relativity describes one of the most well-known forces in the universe: gravity. Quantum mechanics describes three other forces: the strong nuclear interaction, which binds protons and neutrons in atoms, electromagnetism, and the weak interaction, which is involved in radioactive decay. Every event in the universe, from the ionization of an atom to the birth of a star, is described by the interactions of matter through these one forces. Using complex mathematics, it was shown that electromagnetic and weak interactions have a common nature, uniting them into a single electroweak force. The strong nuclear interaction can also be included, but gravity just doesn't join them. String theory is one of the most serious candidates for unifying all these forces. The genesis and challenges of string theory. It's worth noting that in its early days, string theory wasn't taken seriously at all. In the late 1960s, a young Italian theoretical physicist was searching for equations that could explain the strong nuclear interaction, the incredibly powerful glue that binds atomic nuclei by holding protons and neutrons together. He found a 200-year-old equation written by Swiss mathematician Leonhard Euler. This equation, surprisingly, described that very strong interaction. Later, the equation caught the eye of a young American theoretical physicist, Leonard Susskind. He noticed that particles behaved in a way that couldn't simply be point particles. The formula described a thread like an elastic band that could not only stretch and compress but also oscillate and twist. After describing his discovery, Susskind presented the revolutionary idea of strings. Unfortunately, the vast majority of his colleagues met the theory with skepticism. At the time, accepted science envisioned particles as points, not strings. For many years, physicists investigated the behavior of subatomic particles, colliding them at high speeds and studying the consequences of these collisions. It turned out that the universe is much richer than one could have imagined. There was a veritable demographic explosion of elementary particles, but scientists couldn't find an answer to why there were so many and where they came from. This pushed physicists to an unusual and stunning prediction. They realized that the forces acting in nature could also be explained using particles. That is, there are matter particles and there are force-carrying particles. A photon, for example, is a particle of light. The more of these force-carrying particles, the brighter the light. Scientists predicted that this exchange of force-carrying particles is nothing other than what we perceive as a force. This was confirmed by experiments, bringing physicists closer to Einstein's dream of unifying the forces. Scientists believe that if we travel back to the moment immediately after the Big Bang, when the universe was trillions of degrees hotter, the force-carrying particles of electromagnetism and the weak interaction would become indistinguishable and merge into a single force called the electroweak force. The Standard Model, which describes subatomic particles and their interactions, ultimately gained widespread acceptance. But even this perfected theory had one major problem. It did not include the most well-known macroscopic force, gravity. For the yet-to-bloom string theory, autumn arrived. It contained too many problems from its very inception. For example, the theory's calculations predicted the existence of particles that, as was soon established, did not exist. This is the tachyon, a particle that moves faster than light in a vacuum. Among other things, it turned out that the theory required as many as 10 dimensions. Not surprisingly, this greatly perplexed physicists, as it is obviously more than what we see. The revival of string theory and its fundamental constants. By 1973, only a few young physicists were still grappling with the enigmatic calculations of string theory. Among other problems, the equations stubbornly described a mysterious particle that had no mass and was not observed in nature. What could it be? Perhaps the equations of string theory also describe gravity. By assuming that strings are billions and billions of times smaller than an atom, string theorists turned a flaw into a strength. The mysterious particle acted as a graviton, a long-sought particle that would allow gravity to be brought to the quantum level. Every atom, as is known, consists of even smaller particles, electrons, which orbit a nucleus composed of protons and neutrons. Protons and neutrons, in turn, consist of even smaller particles called quarks. But string theory asserts that it doesn't end with quarks. Quarks consist of tiny, writhing threads of energy that resemble strings. Each of these strings is unimaginably small, so small that if an atom were enlarged to the size of the solar system, a string would be the size of a tree. Science today knows a set of numbers that are the fundamental constants of the universe. These are what determine the properties and characteristics of everything around us. Among these constants, for example, are the charge of an electron, the gravitational constant, and the speed of light in a vacuum. If we change these numbers, even by an insignificant amount, the consequences would be catastrophic. Suppose we increased the strength of the electromagnetic interaction. What would happen? We might suddenly find that ions repel each other more strongly, and nuclear fusion, which makes stars glow and emit heat, suddenly fails. All stars would go out. But what does string theory, with its extra dimensions, have to do with this? The point is that, according to string theory, it is the additional dimensions that determine the precise value of these fundamental constants. Some forms of these dimensions cause one string to vibrate in a certain way and give rise to what we see as a photon. In other forms, strings vibrate differently and give rise to an electron. It is these vibrations that create all the fundamental constants of this world. The future of string theory. In the mid-1980s, string theory took on a majestic and coherent appearance. But within this monument, there was confusion. In just a few years, 5 versions of string theory emerged. In some versions, strings had open ends, in others they resembled rings, and in some variants, the theory even required 11 dimensions. The paradox is that all 5 versions can currently be called equally valid. But which one truly describes our universe? This is another mystery of string theory. However, the main problem with strings, as already mentioned, is the inability, at least for now, to prove their existence experimentally. Some scientists, however, still suggest that with the next generation of particle accelerators, there's a minimal but still present possibility of testing the hypothesis of extra dimensions. Although most are confident that if this is possible, it will happen very far in the future, at least decades, and at most even 100 years from now. So, we've tried to explain the famous string theory in very simple terms. I hope everything is clear to you. Please like, comment, and let's discuss. And subscribe if you're not with us yet. We have many interesting journeys ahead. For now, best wishes to everyone, and see you soon.